Hi everyone, it's Mrs. Meehan, and in this screencast, I am going to go over the difference between mass and weight and introduce a type of force called the normal force. As a quick do now, go to the following link when it pops up on your screen and find out what your weight would be on different worlds. So a person's mass in this case is 62 kilograms. They want to know how their mass and weight will be affected by the gravity of 4 different planets: Mars, Venus, Earth, and Jupiter. All you need to do is drag the red point across the 4 different planets and make sure you're looking at what the person's weight is versus their mass. Okay, so overall, what you would have seen is that no matter the planet, the mass of the person did not change, and we'll discuss why in a moment. The weight, however, did. So on Jupiter, you actually weighed the most. And on Mars, this person weighed the least. Some of the objectives for this lesson includes differentiating between weight and mass, describing weight as a force in terms of mass and gravitational acceleration, and describing something called the normal force and understand the conditions in which it exists. So, mass is the measure of the inertia of an object. It is the resistance of an object to accelerate. In the SI system, mass is measured in kilograms. Now, mass is not a weight. You may have heard in common conversation sometimes these two terms being used interchangeably. But scientifically, mass and weight are not the same thing. Mass is a property of an object. It doesn't depend on where the object is located. Weight, on the other hand, is the force exerted on that object by gravity. If you go to the moon, whose gravitational acceleration is about a sixth the gravity, you will weigh much less. Your mass, however, will still be the same. Take a quick moment to check out this video by Veritasium, and then come back to this Edpuzzle. Weight is the force exerted on an object by gravity. Close to the surface of Earth, where the gravitational force is nearly constant, weight can be calculated with the force of gravity equals mass times gravity, or weight equals mass times gravity. So near the surface of the Earth, g, where gravity is equal, or acceleration due to gravity, is equal to 9.8 meters per second squared downwards. Let's try a couple of practice problems. So remember, the force of gravity, otherwise known as weight, is equal to mass times acceleration due to gravity, mg. So determine the force of gravity, or the weight, on a 6 kilogram bowling ball. The correct answer is 58.8 newtons. So 59 newtons for letter C would be the correct answer. So what we're given is 6 kilograms, and we want to find out the weight. Weight is equal to mass times gravity. So 6 kilograms times the 9.8 meters per second squared, which is the acceleration due to gravity on Earth, is equal to 58.8 newtons. Determine the weight of a small car with a mass of 900 kilograms. The correct answer is 8,820 newtons. So choice D here. So we're given 900 kilograms as the mass. What is the weight? The weight is equal to mass times gravity, which gives you 8,820 newtons. Using a spring scale, you find that the weight of a friction block in the lab is 24 newtons. What is the mass of the block in kilograms? The correct answer is 2.5 kilograms. So weight equals mass times gravity. If you're solving for mass, the equation is rearranged to be mass equals weight divided by gravity. So 24 newtons divided by 9.8 meters per second squared gives you 2.5 kilograms mass. An object located near the surface of the Earth has a weight of 245 newtons. What is the mass of the object? So again, you want to rearrange the equation to solve for mass. So mass equals weight divided by acceleration due to gravity, which gives you 245 newtons divided by 9.8 meters per second squared equals 25 kilograms, which is choice A. Which of the following properties of an object is likely to change on another planet? The correct answer here is B. That is the only property that would change based on the type of planet. Since weight is equal to mass times gravity, and gravity will be different on each planet. So that would affect what the weight will be, even though the mass remains the same. The acceleration due to gravity is lower on the moon than on Earth. Which of the following is true about the mass and weight of an astronaut on the moon's surface compared to Earth? So the correct choice here is B. Again, no matter what planet or moon you are on, mass will always be the same. Weight will be different, and in this case, since the acceleration due to gravity is lower on the moon, then the weight will also be lower. Okay, so next I just want to quickly explain another type of force. So we know that an object at rest must have no net force on it. Since it is at rest, there is no acceleration being experienced. If there is an acceleration, there must be a force. But in this case, we have a net force that equals 0. So if it is sitting on a table, the force of gravity is still there. But additionally, what other force is there? It has to equal 0 since the object is not moving. So we know there has to be another force that is opposing the force of gravity. So this other force is exerted in a perpendicular direction to a surface, and it is called the normal force. So the normal force is exactly as large as needed to balance the force from the object. So if the required force gets too big, then something will break. Now, why is it called the normal force? Normal is a synonym for perpendicular. So you could also call it the perpendicular force, but calling it the normal force is the same thing and a lot easier. Let's try a couple more practice problems. So a 14 Newton brick is sitting on a table. What is the normal force supplied by the table? So the correct answer is A, 14 newtons upwards. So this 14 Newton brick, that gives you the weight. So weight is due to the acceleration due to gravity. Since the acceleration is downwards, remember the force will also be in the same direction as the acceleration and vice versa. So that means this force is downwards. In order for this brick to not be in motion, there must be a 0 net force. So the normal force in this case would be a 14 Newton normal force upwards in opposition to the downward 14 Newton force or 14 Newton weight of the brick. What normal force is supplied by a desk to a 2 kilogram box sitting on it? Okay, to solve this problem, let's say we have our desk here. We have a box sitting on it, and that box weighs 2 kilograms. We know that we have the downward force here, mg, mass times gravity, or your weight. And since the box is sitting there, it's not accelerating, that means the net force must equal 0. So the normal force in this case will be equal in magnitude to the downward force, mg. It will just be in the opposite direction. So knowing that, so the magnitude, we'll just stick with that. The magnitude of the normal force is going to be equal to the downward force of mg, which is the weight. So if normal force equals mg, mass times gravity, simply sub in the values. We have the 2 kilograms times acceleration due to gravity, and that should give you an answer of 19.6 newtons, and that will be upward. So remember, it is a vector, so 19.6 newtons upward. Okay, so the practice problems that correlate with this lesson are chapter problems numbers 20 to 31 and multiple choice problems numbers 12 to 20. Let me know if you have any questions on any of these problems that you would like to go over in class.